In this video, we're going to discuss the graphs of polynomial functions. So by polynomial function, we mean we have x raised to a power, but not a negative power because we don't have, we won't have an x in the denominator, for example. And we'll have various power terms being added together, and there'll be constant multiple coefficients. So the graph of a polynomial function will be smooth, meaning it's not going to have any sharp corners like our absolute value function has a sharp corner at the origin. We won't have any sharp corners like that. And it'll be continuous, meaning that we can draw the entire graph without picking up the pencil. So first we're going to look at polynomials of even degree. So the degree of a polynomial is the highest exponent on the variable. So here are some examples of even degree polynomials. The most basic one that we've seen so far is y equals x squared. And so of course we know what that graph looks like. And any polynomial of degree 2 will be a parabola. We've studied parabolas already in quadratic functions. But for higher degree polynomials, the shape of the graph will depend on the function. So even, for example, a fourth degree polynomial can take on different shapes. So here's the graph of negative x to the fourth. So it's a U shape. It's not a parabola. Only quadratics, so only degree 2 functions, make parabolas. But a fourth degree or any other even degree could make a U type of shape. It's not a parabola though. And this is negative x to the fourth, so it's facing down. It's a reflection of just y equals x to the fourth. And then here's y equals x to the fourth minus x squared plus x. So we get a different shape there than we did for the other fourth degree. So once you get higher than degree 2, the shape can vary based on what the function is. Now one thing we're seeing here from these three examples is that the end behavior, so if we look at the ends of the polynomial where the arrows are, for any even degree polynomial, the end behavior will be the same at both ends. So either both arrows will be pointing up or both arrows will be pointing down. We certainly knew this was true about parabolas, but it's going to be true for any even degree function as well. And just like for our parabolas, if our leading coefficient is positive, both ends point up, and if the leading coefficient is negative, both ends point down. This will be true for any even degree polynomial. So we can see here that the first one and the third one, the leading coefficient is positive 1, but for this one, the leading coefficient was negative 1, and so that's the one where both ends point down. So that end behavior is not really anything new. We've seen it in quadratic functions, we've seen it in parabolas, but that will be true for any even degree polynomial. Now let's talk about odd degree polynomials. So we've already seen y equals x cubed. So we're familiar with that shape. But not all cubic functions will have that shape. So for example, here's y equals x cubed plus 2x squared minus x plus 4. So it kind of dips down in that one spot there. So different shape from our y equals x cubed. Switch colors here. Here's a couple 5th degree. So this is y equals x to the 5th plus 3x cubed minus 2x plus 1. It actually looks really similar in shape to the one we just graphed. And I'll squeeze this one down here. This is y equals negative x to the 5th plus 4x cubed minus 5x minus 2. Graph it up here where I have more room. It's not the best drawing on here, but you get the idea. So whereas for our even degree polynomials, the end behavior was the same at both ends, what we're seeing here is that for an odd degree, the end behavior will be opposite. So one end will be pointing down, the other end will be pointing up. And the leading coefficient actually tells us which end points up and down. So if you think about our basic y equals x cubed, the left end points down and the right end points up. If you were to reflect that, so in other words, y equals negative x cubed, it would be the opposite. The left end would be up and the right end would be down if you did that reflection. So the same will be true for any odd degree polynomial. The left end down, right end up for a positive leading coefficient, and then we saw here for a negative leading coefficient it will be the opposite. So that's not too hard to remember if you're familiar with the graph of y equals x cubed. If you picture that, that will help you remember which end is up and which end is down for a positive leading coefficient. And then it's the opposite for a negative leading coefficient.